Hello all. In this video we're going to be looking at something which is actually completely new. So those of you who have been waiting for something that is not just a rehash of what you've done in middle school, congratulations, you've made it. We're going to talk about something called an exponential function. And this is an entirely different class of functions. We've seen two classes so far. We've seen linear functions, which form a straight line, and absolute value functions, which form like a V in their graph. And now we have a third type that we're going to add called an exponential function. And here's how an exponential function works. And this is what I want you to get out of the video, if nothing else, is I just want you to understand where how an exponential function is built from all its parts. So let's start with those parts. We have three parts that we're going to look at. The first is called the initial value. So we're going to have some starting amount, whatever it is. So in this case, let's start with 2. So I'm going to have some initial value of 2. And to build the rest of the function, what I do is I multiply that 2 by some number. And we're going to call that number that I multiply by a base or a growth factor. And I'm going to use 2 as my growth factor as well. So I'm starting with 2. And now I'm going to use a growth factor of 2, which means I take the 2 that I started with, and now I'm going to multiply by 2. So 2 times 2 is 4. Every time I do this is called a growth cycle. So just to recap really quickly, I have my initial value, which was 2, and then I have a growth factor, which is also 2, which means every time I want a new number, I'm going to multiply the old number by 2. So I took 2 times 2, which is 4, and now I'm going to multiply by 2 again. 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. And you'll notice that as we go, this is starting to get very big very fast. The next two terms in this sequence would be 64 and 128. So this thing grows really quickly. That's called exponential growth, named after this type of function. So again, we have an initial value of 2. And then I took that initial value and I multiplied it by 2 each one of these times. So that means our base or our growth factor is 2. And I did this 1, 2, 3, 4 times. So I can say I would have 4 growth cycles. So each time you multiply by the base, we have what's called a growth cycle. And you can do this, and here I've built a sequence for an exponential function. And we can also put this in a table or in a graph, and that's what we're going to look at as we go forward. So some important notes, things you have to remember about these exponential functions. For now, just write these down and know that they exist. We'll come back and we'll explore these a little bit later with Desmos. But the base or the growth factor can't be negative, 0, or 1. So it can't fit any of those. The initial value can't be 0. And if the base is between 0 and 1, we'll get this graph that kind of curves downwards. Instead of getting bigger, the numbers will get smaller, and we call this exponential decay. So now let's look at how this is different from something we know about, a linear function. So here I have the beginnings of a linear function and the beginning of an exponential function. I can see the y-intercept, where x is 0 for this linear function is 3. The y-intercept for my exponential function is 3 as well. But we can see too that the second term is the same. So 3, then 6. But as we go through these, we're going to see that they start to diverge wildly. For a linear function, the next term would be 9. For my exponential function, the next term would be 12. And if I go one more, for the linear function, the next term is 12. And for my exponential function, the next term is 24. And here we can see one of the key properties of exponential functions. That is, when the base is positive, these exponential functions get very, very big, very, very fast. Notice that by the time we get to x equals 3, the linear function is up to 12. The exponential function is up to 24. And it's just going to get worse the farther we go down. These numbers are going to get very large very quickly. But more importantly, let's check this out. For the linear function, we have what's called a slope. And every time the x changes by 1, we add this slope, in this case 3, to the y value. So each time I just added 3 to my initial value, my y-intercept. So 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12. For an exponential function, however, I'm not adding, but rather I'm multiplying. So 3 times 2 would be 6. And then I multiply by 2 again. That would give me 12. And multiply by 2 again. That's where the 24 comes from. So we can see that in a linear function, we are adding. In an exponential function, we're multiplying. And again, I have my initial value, my starting point. I have my base, my growth factor. And I've done this 3 times. So as I said before, the key difference here is that in a linear function we add or subtract depending on whether the slope is positive or negative. And in an exponential function we're going to multiply, or we can also divide if we have exponential decay. Rather than multiply by some number, I can divide by some number as well, making this smaller. So here we can see a linear function with a slope of 3 where I add 3, and an exponential function with a growth factor or base of 3 where I'm multiplying by 3 each time. And you can see just how much faster this exponential function gets large due to the fact that we're multiplying instead of adding. Alright, let's switch gears, talk about the graphs of these for a second. A linear function is very easy to identify from its graph. It's linear, that is, it makes a straight line. So all linear functions are going to have a straight line. The absolute value function, you'll remember, formed like a V shape. And this is what our exponential function is going to look like. It's going to have a curve. It'll look a little like a boomerang almost. And it can curve up or it can curve down. But it will have some sort of curve to it like this. Again, almost like a boomerang. So let's take a look at this and let's see if we can look at these 3 functions, f of x, g of x, and h of x, and determine which one of these is exponential as opposed to linear. Remember, if it's exponential, you're going to be multiplying by some number each time. So a good place to start is whatever's first in the chart. Here I start with 0, and so if this is exponential, I'm going to be multiplying something times 0 to get 3. And here we immediately see the problem. There's nothing you can multiply 0 by that's ever going to give you 3. So there's nothing I can multiply there. So this cannot be an exponential function because we're starting off with this 0. It has an initial value of 0, which you'll remember is not allowed. So even though this does look like something that's getting large fast and is multiplying, there's not any constant thing that I can multiply this by for it to be an exponential function. So let's take a look at g of x. Maybe it's an exponential function. I'm starting with 2 as my initial value, where x equals 0. And to get from 2 to 4, I'm multiplying 2 times 2. Well, let's see if that holds up. 4 times 2 is 8. 8 times 2 is 16. So I'm multiplying by 2 every time my x value increases by 1. So g of x is an exponential function with a growth factor of 2. Over here, I can look and I need to find some number that I can multiply -5 by to get -2. Nothing immediately comes to mind, so let's pick an easier situation. 1 and 4, well, if I take 1 times 4, that would give me that. So we have to see if that holds true everywhere else. -2 times 4 is distinctly not 1, so h of x would be not exponential. So the only one of these we have that is exponential is g of x, because we're multiplying by some number each time. If we look at these graphs, we can then determine which one of these is going to be exponential. Remember, exponential has a curve that kind of looks like a boomerang. This has a nice curve to it, but it's curved on both sides. This is what we call a quadratic. This has a nice curve to it, but it's not that boomerang shape we're looking for. Look at j of x, though. That nice smooth boomerang going up really fast. That, friends and neighbors, is an exponential. And k of x, you can see, is just a linear function. Next, let's talk about the initial value a little bit more. The initial value is simply the value of the range, so the y value, when the x value, the domain value, is 0. This is the exact same thing as a y-intercept. There's no difference between the two. So I can immediately look at this one and I can see my y-intercept is 2. So my initial value for this function would just be 2. Over here, this table actually corresponds to this graph, but I can see if I'm looking for the y-intercept, I want to find the y value, which is over here under the g of x heading, the y value when x equals 0. So x is 0, so the y value that goes with that is 2, so my initial value, also called the y-intercept, is 2. Do not make the mistake of thinking that this is just going to be the first thing in the table. It is not necessarily the first thing in the table. It is the one that is paired with 0. Now in this case it does happen to be the first one in the table, but you're looking for the one paired with 0. And then finally we have our base, the growth factor. This is the amount that you're multiplying for every change in x. So if I look at this graph, this is tricky to find on the graph, but my y-intercept is 2. And if I go over one space, my y value is now 4. So to go from 2 to 4, I have to multiply by 2. Remember, this is exponential, so we're looking to multiply. So 2 times 2 would give me 4. So the growth factor here is 2. In the table, it's maybe even easier to see. I can just see that I'm multiplying each one of these numbers by 2 to find the next number. So my growth factor would be 2. All right, that's it for exponential functions. The graph of an exponential function is a curve. It starts at some value called the initial value, also called the y-intercept. And from there, you take that y-intercept and you multiply that value by some number called a growth factor. You can also divide if it's getting smaller. And the number of times you do this is called the number of growth cycles that happen in the function.